2 pi. So what I'm trying to show you here is that if you change your phi variable value from 0 to 2 pi here, you are tracing out a circle like this. You are tracing out a circle coaxial with the z-axis. You are tracing out a circle coaxial with the z-axis. So the coordinate variable phi, as you vary from 0 to 2 pi, you are tracing out a circle coaxial with the z-axis, and this circle is the coordinate line. This circle is the coordinate line corresponding to phi variable. So you see that the coordinate line corresponding to phi is no longer a straight line. It is a curved line, or it is actually a circle. Curved line or a circle. Now the theta coordinate variable also, as you see, theta equal to 0 is along the z-axis. As you move away from the z-axis like this, your theta value increases, and on the xy plane your theta value will be 90 degree. And if you continue and towards the back side or the lower side of this xy plane, you can extend up to, as you extend up to pi here, you will be touching the negative z-axis. You will be touching the negative z-axis there. So it would be like when you vary your theta value from 0 to pi, you are tracing out a curved line from this to this. You are tracing out a curved line from this to this. So you can see that this theta coordinate variable or the theta coordinate line is also a curved line. It is a semicircle. Because you are tracing from 0 to pi, you will cover semicircle only. So theta coordinate line is a curved line. And what will be the coordinate surface? Now let me write a certain picture here. I think this will help if I write a picture here. Let's say you fix the value of r equal to c, r equal to c1. If you fix the value of r, that is the radius is fixed, the radius or the distance of the point from the center is fixed. If you are allowed to vary phi from 0 to 2 pi and theta from 0 to pi, theta from 0 to pi, by fixing the value of r, you will be able to cover every point on the surface of a sphere. Fixing the value of r means you are fixing the radius of the sphere. So at any point on the surface of the sphere, your r value will still be c1. If you take any point on this surface of the sphere, if your r value is fixed, right? So the coordinate surface corresponding to corresponding to r equal to c1 is a sphere of, it's a sphere of fixed radius. Okay, it is a sphere of fixed radius. R equal to c1 is a sphere of fixed radius. So you take any point on the surface of the sphere, your r value is always constant. Your r value is same all over any points on the surface of a sphere. Now let me make one blank space once again. Yeah. Now let us see the next coordinate surface, which is phi equal to c2. Phi equal to c2. So if you fix your phi value, phi as fixed, phi as fixed means you are considering if you can vary r from 0 to infinity, you can picture a certain kind of plane like this, a certain kind of plane. So if you fix the value of phi, you will get an infinite plane. You will get an infinite plane touching the z-axis. This is an infinite plane extending up to infinity. Extending up to infinity, that means it is an infinite plane touching the z-axis. So you have this z-axis. If you fix the value of your phi at a certain constant, you will get infinite plane touching the z-axis. That is another coordinate surface. And another coordinate surface we can consider is fix the value of theta. If you fix the value of theta, what kind of surface we will be getting, whether we will be getting a plane or a curve surface. Let us see. So this is x, y, z. Now if this is your r, if you fix your value of theta equal to c3, and if you can vary your r from r can vary from 0 to infinity, that means r can extend up to infinity. It can go up to infinity. And you can vary your phi from if you can vary phi from 0 to 2 pi, that means you can move this infinite line around the z-axis. So if you move this infinite line around the z-axis, you will get a infinite cone. So the surface is coordinate surface corresponding to this is infinite cone having vertex at the origin. This is the origin. Okay. Here, if you can vary your r value from 0 to infinity, and you can vary your phi value from 0 to 2 pi here, if you fix the value of theta, you will get an infinite cone having its vertex at the origin. This is your vertex, okay, of the cone. So here now you see that this is also curved surface. This is also curved surface. So what are the surfaces we have talked about? The first coordinate surface we talked about was fixing the value of r. When you fix the value of r as c1, you get a sphere of fixed radius. So r equal to c1 surface is a curved surface. R equal to c1 surface is curved surface. And similar to that, we have also discussed phi equal to c2 when you fix the value of phi, and you can vary your r from 0 to infinity, and your theta from 0 to pi. You will have an infinite plane touching the z-axis. And when you fix the value of theta at c3, you will have an infinite cone. So this is also another curved surface, right? So these are the coordinate surfaces for a spherical coordinate system. Now, once you obtain the scale factors, you can also obtain the unit vectors, tangential unit vectors, as I discussed. So simply you have to differentiate and divide with the magnitude. The magnitude of the tangential vector is your scale factor, your HR, h theta, and h phi. And you can obtain all these unit vectors. And this is another example which you can work it out yourself also. You can see that the spherical system is an orthogonal system. You can show that the spherical system is an orthogonal system. How do we prove that the spherical system is an orthogonal system? You have to take the dot product of all the unit vectors the dot product between the unit vectors. When you take the dot product between the unit vectors, if the dot product result comes out to be 0, then this shows that the angle between these two unit vector is 90 degree, that is orthogonal. The dot product, if it comes out 0, then the angle between these two unit vectors is 90 degree. So when the unit vectors along the coordinate lines are mutually perpendicular, the coordinate system is considered as a orthogonal system. The coordinate system is considered as a orthogonal system. Okay, so these are simple mathematical steps. You can do it yourself now once you have the unit vectors. Now let us move on to the last section of our syllabus, that is the tensor analysis. So this particular unit 3 is a little bit vast, or it's a little bit heavy. Actually, the first section was vector analysis, that is we define gradient, divergence, and curl, and then we continued with vector integration theorems like Gauss's theorem, Stokes theorem, and Green's theorem. And after that, we jumped into the curvilinear coordinate system. And in the curvilinear coordinate system, we focus on orthogonal curvilinear coordinate system. And we also discuss about this cylindrical system and spherical coordinate system. Now this is the last part, that is the tensor analysis. Here we will talk about basic ideas on tensor. So this is just to give you a certain basic idea on tensor, because say in elementary physics we classify our physical quantities into two broad, very broad classification called scalar and vectors. So every physical quantity we have encountered so far, we can classify it as a scalar or vector. If the physical quantity we consider or we encounter is not having any direction, then this is called scalar. Like we discussed energy, and also we have talked about temperature of a room. Also, any point in any particular point in the within a room, you will have a certain value of temperature, but it does not have any preferential direction, or it does not have any direction. So its temperature, it only has a magnitude. So this kind of quantities are called scalars. And we also have a vector quantity like velocity or force, because whenever you are talking about force, you have to consider the direction of application of force. You have to consider the direction of application of force. Okay, so like that, you can uh, see that certain physical quantities will have their direction, and however other physical quantities may not have any direction. So they are what you call it as a uh, scalars and vectors. Like in the Ohm's law also, we know that uh, current is directly proportional to the applied electric field. Uh, so this is the Ohm's law expression in terms of current density. J is called the current density, E is electric field. So this is this mathematical form which is expressed in terms of like current density and electric field. This is another form of Ohm's law. Actually, Ohm's law, as you know, it's V is equal to IR, where V is the voltage applied, I is the current, and R is the resistance. And then you can write I as V upon R, and you can divide with area, cross-sectional area, 1 upon R into V upon cross-sectional area. And you can write R in terms of resistivity again. Resistivity is directly proportional to length, inversely proportional to cross-sectional area, and the proportionality constant is resistance. So like that, you can, no, not like this, sorry. The resistance of a material is directly proportional to length and inversely proportional to cross-sectional area, and the proportionality constant is called your resistivity. So you can express your R in terms of your resistivity, and reciprocal of resistivity is what we call as a conductivity of a material. So if you continue that here, it will be I upon A is your current density called J, and uh, R is rho L upon A, and V is V upon A is there, so A and A will cancel out. So J is equal to 1 upon rho is known as the conductivity. Reciprocal of resistivity is conductivity J, sigma. Voltage upon length. Applied voltage upon length is the electric field. Okay, so electric field is a vector quantity, and current density is also a vector quantity. Current will flow along the direction of application of electric field. So we classify this as a vector quantities, electric field and current density. And the proportionality constant is sigma, the conductivity. So under normal circumstances, like in a certain material which does not have any preferential direction, this sigma is a scalar quantity. Sigma is simply a scalar quantity. Like that means if you write your current density vector in terms of the coordinate components jx, jy, and jz, you can write it as jx I cap, jy, j cap, k cap. These are unit vectors. And your electric field in terms of the coordinate components ex I cap, ey j cap, e cap, ez k cap. So if this relation holds, then you can write this as, let me use another blank page here. Yeah, if this relation holds, you can write this as jx I cap plus jy j cap plus jz k cap sigma ex I cap plus ey j cap plus z k cap. Now from this you can see that the I component the will be jx equal to sigma ex, jy is equal to sigma ey, jz is equal to sigma ez. So in isotropic crystals or in any isotropic materials which does not have any preferential direction, this will be the relation, that is j vector will be equal to sigma of e vector. So jx is proportional to the electric field applied along x direction. Jy, the current density along y direction, is proportional to the electric field along y direction, and similarly the current density along the z direction is proportional to the electric field applied along the z axis, and the proportionality constants are all sigma, the conductivity of the material, which is a scalar quantity in isotropic material. But later on you will come across in material science there are certain materials which are anisotropic. There are certain materials which are anisotropic. So anisotropic means it has a preferential direction. So in such material we cannot consider sigma as a constant, or this relation j equal to sigma e no longer holds. Okay, so here if you write j as j1 I cap plus j2 j cap plus j3 k cap, your j1, the component of current density along the x-axis will now be this. So the previous relation that was J1 was sigma E1 no longer holds. Okay, this relation no longer holds. So now J1, the current along the x-axis, the I cap direction, is not only determined by the electric field along the direction. That current J1 along the x-axis, along the I cap direction, is also influenced by electric field along y direction, also influenced by electric field along z direction, influenced by electric field along x, y, and z. So you can see that similar to that, the component of the current density along the y direction, that is your J2, is no longer simply proportional to your electric field along the y direction. This relation no longer holds. Here, in such an isotropic crystal, your current density along the y direction is also influenced by the electric field along the x, also influenced by electric field along the z. So the proportionality constants for each electric field can be written as sigma 11, sigma 12, sigma 13, and similarly sigma 21, 23. So this sigma, the the conductivity, as you see, it is no longer a constant quantity for every component of the current density, or for every component along the electric field direction. So they can be now written as this. Uh, it now, as you see, it now has 9 components. The current density now has the conductivity now has 9 components. So this conductivity is known as a conductivity tensor. So this physical quantity, the conductivity, as we know it, it is no longer a scalar, nor it is no longer a scalar nor a vector. So we cannot classify this conductivity of anisotropic crystal as a scalar or vector. So we need another like another classification, or another category to identify such kind of physical quantity, which are beyond your scalar and vector concepts, are known as tensors. Or in fact, later on we will see that like all the scalar quantities and vector quantities are also a special case of tensor. So in higher physics, we can represent any engineering or physical quantities as a tensor. Any engineering or physical quantity, we represent it as a tensor. And certain physical quantities which are represented as tensor, if you consider a special case, then they can be classified as scalar or vector. So this tensor is a very broad representation, or mathematical representation of physical quantities, broad mathematical representation of physical and engineering quantities, physical quantities. And vector and scalar is a certain special case of a tensor. So later on we will see that tensor of zeroth order is scalar. Tensor of first order is vector. Tensor of first order is vector. And there can be higher order tensor also with higher number of indices, like for example here in this case, this conductivity tensor, it can be represented using 2 indices here. So this is called second order, like that. So I think I will stop here, and I will not take class tonight. Most likely tomorrow I will see convenient time, then I will announce for a class. Okay, I will stop the session now. You can exit the meeting.